NASA confirmed Thursday that the Voyager 1 probe has made history by becoming the first human-made object.
Voyager 1, humanity's most distant emissary, has once again stunned the scientific community. After nearly 5 decades of traversing the vastness of space and now floating over 15 billion miles from Earth, this tireless spacecraft has transmitted data that defies the expectations of both astrophysicists and engineers. Experts are calling it an impossible discovery, something completely unforeseen and potentially revolutionary, as it challenges long-held beliefs about the nature of space beyond our solar system. Since crossing the heliopause in 2012, the boundary where the Sun's influence gives way to the interstellar medium, Voyager 1 has provided invaluable insight into the mysterious region between the stars. While entering interstellar space was a milestone in itself, Voyager 1 has now detected a persistent, organized structure in the deep space plasma, a coherent, oscillating wave of charged particles extending hundreds of millions of kilometers. Initially dismissed as a possible instrumentation fault, understandable given the spacecraft's age and exposure to cosmic radiation, these waveforms turned out to be real and coherent, not the product of malfunction. This revelation shocked scientists, who long assumed the interstellar medium to be a quiet, mostly homogeneous environment composed of sparse hydrogen, helium, and cosmic rays. But Voyager's data now suggests the medium is not only dynamic, it is organized, resonating with a precision and regularity not previously thought possible. The oscillations Voyager detected don't match any known phenomena such as solar shock waves or magnetic turbulence. Instead, they resemble standing waves, akin to those found in crystal lattices, but spread across the vastness of interstellar space. This implies new, unknown physics may be at play, forcing scientists to reevaluate how energy and matter behave beyond stellar influence. If these waves are widespread, interstellar space might be far more interconnected than previously believed, hinting at matter and energy interacting across light years. The discovery renders the idea of a void obsolete, replacing it with a vision of space as a resonating, structured medium. Speculation abounds. Are these waves the result of magnetic reconnection events sparked by ancient supernovae, or ghostly remnants of long-dispersed interstellar shocks? Perhaps even more fascinating is the idea, still highly speculative, that these waves might not be natural at all. Some researchers have begun to entertain the possibility that the harmonic, regular structure of the oscillations could point to engineered origins. If intelligent life once existed elsewhere in the galaxy, it might communicate not through radio or light, but by subtly modulating the interstellar medium itself. Voyager 1, by sheer chance, may have drifted through one of these hidden signatures. Whether natural or artificial remains unknown. The implications are profound. If coherent structures exist throughout interstellar plasma, they could influence the evolution of galaxies, the transport of energy, the movement of cosmic rays, or even the birth of stars. For planetary scientists and heliophysicists, Voyager's discovery changes how we understand the heliopause, not as a clean divide, but a porous transition between two dynamic realms. Even engineers are amazed, as the spacecraft's 1970s-era instruments continue to perform far beyond their intended lifespan. The plasma wave subsystem, built to study planetary environments, is now detecting the architecture of deep space itself. Voyager 1's success underscores the importance of long-duration missions and resilient spacecraft design, influencing how we'll build future probes meant to journey beyond the solar system. More than just a scientific triumph, Voyager 1 is a symbol of human curiosity and determination. Built during an era of analog dials and slide rules, it now sends whispers from the edge of the unknown. That a tiny machine powered by less than a household light bulb could detect something so unexpected, so profound, speaks to the enduring power of exploration. The discovery also renews interest in SETI and the search for extraterrestrial intelligence. If plasma can serve as a medium for transmitting complex information, whether natural or artificial, then perhaps communication isn't confined to light and radio, but occurs as structured energy embedded in space itself. Voyager may have recorded the first evidence of such a whisper. Whether this discovery is a natural phenomenon or something more intentional remains uncertain, but astronomers are eager to investigate further. Voyager 2, which is also in interstellar space but on a different trajectory, has yet to encounter similar waveforms. This raises new questions. Are these structures localized? Is Voyager 1 uniquely positioned to detect them? Or do the spacecraft differ in sensitivity? As theorists begin to explore the implications and engineers contemplate new missions tailored to detect these waves, one thing is clear: Voyager 1 is no longer just a messenger from Earth. It is now a listener, tuned to the deep and ancient rhythms of the cosmos. Invigorated by Voyager 1's astonishing discovery, scientists are now modeling plasma behaviors never before replicated in Earth-based laboratories. Simulations of interstellar turbulence, once a niche area of astrophysics, are now receiving serious attention. The idea that the interstellar medium could host coherent, wave-like structures has sparked comparisons to phenomena such as quantum fluctuations, Bose-Einstein condensates, and even early universe field behavior. Some theorists suggest that what Voyager 1 detected may be a faint echo of cosmological processes dating back to the galaxy's very formation. For physicists pursuing a unified field theory or deeper connections between gravity, electromagnetism, and quantum mechanics, this finding might represent a rare natural laboratory. These interstellar waves could serve as real-world data points to validate or challenge theories that have thus far remained purely mathematical. In its endless flight, Voyager may first have stumbled upon a subtle thread in the code of existence, a piece of the universe's operating system. There's poetic irony in the fact that such a monumental discovery didn't come from a cutting-edge satellite or billion-dollar observatory, but from a 1970s spacecraft launched in the era of disco and analog dials. Once thought to be a fading relic, Voyager 1 has become a wellspring of revelation, venturing farther than any human-made object, and now, deeper into the mysteries of space itself. As data continues to stream in, scientists are preparing for what could be the most groundbreaking phase of Voyager 1's mission. Some speculate the spacecraft might encounter even more of these plasma structures or pass into a region where the oscillations become denser, more complex, and perhaps reveal regions of heightened energy or matter. There's even the tantalizing possibility that Voyager may drift into a space where matter behaves in ways that challenge modern physics. Though Voyager's path can no longer be altered, set only by past gravitational encounters and inertial momentum, the universe ahead is anything but inert. This discovery proves the cosmos is alive with secrets, often revealed not through spectacle but persistence. The faint, rhythmic signal Voyager 1 captured, initially dismissed, has now become impossible to ignore, carrying the weight of scientific revolution. This realization has sparked collaboration across disciplines beyond astrophysics. Plasma physicists, signal analysts, quantum theorists, and even linguists are studying the data, each offering unique hypotheses about what might be encoded in the waves. At the center of this intrigue lies a provocative idea: the interstellar medium might not just be reactive, it might be communicative. The rhythmic oscillations suggest underlying laws yet to be articulated. Perhaps Voyager 1 isn't just drifting through a passive void but is interacting with a spatial architecture, a scaffold shaped by magnetic fields or galactic currents on an unimaginable scale. Specialists in magnetohydrodynamics are proposing that filamentary or lattice-like magnetic patterns could structure plasma resonance points across space, and Voyager may have just passed through one such harmonic node. If more exist, these points could be organized like stations along a galactic frequency spectrum. Even time itself is being reimagined in this context. Could these plasma structures pulse according to a cosmic rhythm, driven by galactic rotations or star formation cycles? The temporal consistency in Voyager's data suggests a long-lived, self-sustaining wave system, something akin to an interstellar heartbeat. Scientists are now combing through past data from Pioneer 10 and 11, hoping to find even the faintest trace of similar patterns to corroborate the discovery. The concept of interstellar weather has evolved too. These plasma waves may influence particle motion across vast distances, subtly shaping the paths of cosmic rays and perhaps solving long-standing mysteries around their irregular arrival on Earth. This also opens new doors for space exploration. If the interstellar medium is not uniform but instead composed of electromagnetic terrain, future spacecraft might be able to navigate, or even surf these plasma waves, similar to how ancient sailors read ocean currents. This would mark a revolutionary step in propulsion, using space itself as a dynamic medium, potentially reducing or eliminating the need for onboard fuel. Plasma structures might also be used for orientation, acting as natural galactic landmarks. Voyager's data could serve as the first draft of a cosmic navigation chart, a kind of texture map of space. Another stunning implication touches on biology. The interstellar medium has long been considered too cold, sparse, and hostile to support life. But if these energetic plasma regions offer pockets of stability, perhaps they provide microenvironments where extremophile organisms, or dormant lifeforms like spores, could persist or even migrate. These waves might act as natural accelerators or preservation chambers, lending new credence to panspermia, the theory that life could travel between stars. The discovery also reframes how we think about galactic history. If these structures are stable or cyclical over millennia, they could serve as records of past stellar cataclysms, preserving echoes of supernovae, magnetar flares, or ancient solar storms. Voyager may first have entered a spatial fossil, a chronicle of cosmic memory etched in plasma. In this light, the spacecraft is not just a harbinger of future discovery but a reader of the universe's deep past. The pulse patterns it detects, either fully random nor entirely regular, are of special interest to information theorists. These low-entropy signals bear resemblance to purposeful communication, structured, intentional, and deeply meaningful. The idea that the universe itself might communicate using low-entropy signals, whether biological, digital, or otherwise, has opened extraordinary avenues for scientific thought. Rather than sending messages via traditional light-speed communication, information could be impressed directly onto the interstellar medium, waiting patiently for those with the right tools and insight to decipher it. In light of this, institutions worldwide are investing in advanced detection technologies to read this cosmic medium with unprecedented fidelity. Proposed instruments for future missions aim to map plasma oscillations in high resolution, while Earth-based observatories are being reconfigured to detect such structures indirectly, possibly through their interaction with cosmic rays or background radiation. Laboratory simulations have also begun, attempting the Herculean task of recreating the interstellar conditions under which these oscillations arise. Culturally and existentially, Voyager 1's discovery has caused a ripple effect. Artists, writers, and philosophers are embracing the notion that space isn't an empty void but a living, breathing system. This challenges long-standing ideas about isolation and even life itself. If the universe is filled with organized motion, perhaps it is not as cold or indifferent as once imagined. There may be an intrinsic harmony, an unseen structure of cosmic order, that connects all things. The concept of a silent universe is now under serious scrutiny. For decades, skeptics of extraterrestrial intelligence pointed to the absence of deliberate, detectable signals as evidence of cosmic loneliness. But what if civilizations never used radio or light-based transmissions at all? What if they imprinted information directly onto the medium of space itself? Though Voyager 1's detected signal has not been confirmed as artificial, its structured nature has already inspired new frameworks for interstellar communication. Instead of antennas, future searches for intelligence may rely on plasma wave detectors. Academic institutions are now launching cross-disciplinary initiatives, combining plasma physics, AI-driven signal analysis, and astrobiology, to explore these implications. Some programs are even investigating whether this discovery could inform quantum communication models or help explain dark matter. While many of these theories remain speculative, they reflect the transformative potential of Voyager 1's unexpected findings. Public response has also been profound. Schools and universities are updating curricula to reflect this dynamic vision of interstellar space. Museums are designing interactive exhibits to help people experience the invisible oscillations Voyager recorded, using sound and light to make these distant patterns feel real. Voyager 1 has once again become a symbol, no longer just of engineering endurance, but of cosmic curiosity and humility. And perhaps the most astonishing aspect of the entire event is its quietness. The signal Voyager 1 detected did not arrive with fanfare or alarms. It was found in subtle modulations, minute shifts in frequency and amplitude, that required patient, persistent observation. It is a powerful reminder: the universe does not always shout. Sometimes it whispers, and only those who truly listen can hear. Looking ahead, missions specifically designed to follow Voyager 1's path are being proposed. Equipped with more sophisticated instruments, these missions aim not only to confirm the findings but to map the plasma structures in 3 dimensions. With a clearer understanding of their spatial orientation, density, and coherence, scientists may eventually simulate their behavior, origins, and future evolution. Meanwhile, Voyager 1 continues its silent drift into deep space. Though its power supply is dwindling and instruments may soon fail, its legacy is secure. By discovering structured plasma oscillations in the interstellar medium, Voyager 1 has redefined not just where we look, but how we look. It has reshaped the architecture of scientific thought, added new chapters to textbooks, and revived the dream of exploring beyond our solar neighborhood. This may be just the beginning. Voyager 1's discovery could be the first of many that change how we understand the galaxy. It may take decades, or centuries, to fully grasp the meaning of these plasma waves, how they form, how they behave, and what they imply about the universe. But the journey has begun. The boundaries of human ignorance have shifted outward again, pushed by a machine that was never designed to go this far, yet has become a witness to the unknown. Voyager 1 did not set out to find what it found. It wasn't built to hear the universe's pulse or to reveal structures beyond imagination. And yet, by enduring, by simply being where it has revealed a universe that is not empty, not silent, and not still. The interstellar medium, it turns out, is vibrant, structured, and possibly even encoded. As we await each new transmission, decoding every hum, every whisper, we are reminded that the greatest discoveries are often the ones we never meant to make. Voyager 1 has touched something ancient, something vast, and in doing so, it has redefined the edge of human knowledge, not with noise, but with a signal drifting endlessly across the dark. Still voyaging through the ink-black canvas of space, Voyager 1 continues not only as a marvel of endurance but now as a probe bearing witness to the unknown. The structured plasma oscillations it has detected hint at deeper organization within the galaxy, perhaps an invisible skeleton beneath what we thought was a random expanse. What started as a curious anomaly has become the centerpiece of a mounting scientific paradigm shift. In the wake of confirming the signal's authenticity, international collaborations have mobilized. Space agencies, observatories, and universities are developing strategies to assess the broader implications of the discovery. One top priority is to map the spatial distribution of these oscillations, using high-resolution simulations of galactic magnetic fields and particle dynamics. The challenge is immense. Voyager's detection radius is infinitesimal compared to the scale of the Milky Way, akin to analyzing an entire ocean from a single droplet. To overcome this, researchers are cross-referencing data from cosmic background radiation, anomalies in fast radio bursts, FRBs, and gravitational lensing, hoping to detect similar waveform patterns across the sky. This might allow them to construct a frequency map, a spectral geography of the galaxy. The implications extend to star formation. Stars form in dense molecular clouds influenced by shock waves, magnetic fields, and turbulence. If structured oscillations are widespread, they might act as seeding mechanisms, triggers for gas cloud collapse. In this sense, Voyager may first have recorded more than a passive waveform. It may have captured an electromagnetic fossil of a star's conception. Understanding how these waves influence cloud behavior could revolutionize astrophysics. Another exciting concept is the idea of phase coherence in interstellar plasma. Unlike solar plasma, which behaves chaotically, the structure Voyager 1 found appears stable and phase-aligned, suggesting an underlying magnetic architecture that keeps the wave intact. These zones might function like galactic tuning forks, resonating subtly across eons. The age of these structures is now under intense study. Are they recent fluctuations caused by nearby events? Or are they ancient relics, imprints left during the Milky Way's formation? Some cosmologists propose that these plasma waves could be a form of spatial memory, an enduring record of galactic history etched not in stars, but in fields. The philosophical implications are staggering. What if the interstellar medium is not just a backdrop, but a cosmic memory system, a living archive of everything that has ever happened? Voyager may first have brushed against this memory, revealing that the void is not void at all. It is filled with resonance, with harmony, perhaps even with messages waiting to be understood. Just as archaeologists read layers of sediment to reconstruct Earth's history, future scientists may one day interpret the waves discovered by Voyager 1 to piece together events from millions, or even billions, of years ago. These waveforms could hold the echoes of ancient cosmic phenomena such as the death of stars, the passage of rogue black holes, or even the formation of spiral arms within galactic structures. Beyond offering a window into the distant past, these oscillations might also unlock revolutionary technological possibilities. One emerging concept is energy harvesting. If certain regions of space are filled with coherent plasma oscillations, could a spacecraft with advanced instrumentation extract usable energy from them? Though it may sound like science fiction, early prototypes of plasma wave collectors have already demonstrated that, under the right conditions, low-energy plasma can be converted into electrical current. Applying this technology to deep space would require significant breakthroughs in materials science and wave resonance tuning, but Voyager's discovery gives this idea a compelling foundation. Another promising area of study is interstellar signal topology, which explores whether plasma wave signatures might carry layered data. In this paradigm, information would not be encoded as binary bits but as modulated waveforms across multiple harmonics, much like how audio is compressed into a rich spectrum of tones. Interstellar space, then, could serve as a medium for transmitting complex data packets over vast distances with minimal signal degradation, something not possible with conventional light-based communication. Intriguingly, Voyager 1's data revealed that the detected waveform exhibited multiple layers, each cycling at different frequencies and overlapping in perfect harmony without canceling each other out. This opens the door to new forms of data encoding that current SETI methods might entirely miss. If an intelligent civilization were using plasma waves to communicate, we may have overlooked their signals, not because they weren't transmitting, but because we weren't listening at the correct frequency or dimension. The structured plasma Voyager 1 passed through could have been shaped not solely by natural phenomena, but perhaps even by deliberate design, whether as a beacon, a marker, or a message. Yet, even if these waves are entirely natural, their very formation suggests an interstellar medium far more dynamic and organized than previously believed. Interstellar turbulence, once assumed to be purely random, may, under certain conditions, self-organize into coherent structures. This phenomenon, known as emergent behavior, occurs when simple rules at small scales generate complex patterns at larger ones. It's a concept observed in everything from weather systems to neural networks. If interstellar plasma demonstrates similar emergent properties, it fundamentally challenges long-standing assumptions that order cannot arise from such diffuse and chaotic conditions. Voyager 1's findings may not only redefine our understanding of space but also the very nature of complexity in the universe. If you found this discovery as fascinating as we did, please like this video, subscribe to our channel, and share your thoughts in the comments. What do you think about Voyager 1's impossible deep space discovery? And what might be next? Thank you for watching, and we'll see you next time.